Learning objectives. At the end of this topic, you will be able to explain magnetic field and field lines, draw magnetic field lines of a bar magnet, analyze the pattern of magnetic field due to current through a straight conductor and circular loop, state and explain right hand and left hand thumb rule, analyze the pattern of magnetic field due to current in a solenoid, analyze the force on a current-carrying conductor in a magnetic field. Introduction. Rita and her friend Sheila.
If we place horizontally a small compass near this copper wire and pass the current through the circuit by inserting the key into the plug, we observe the position of needle is changed. Can you tell me why it happened? We see that the needle is deflected. Right. What does it mean? I don't know. It means that the electric current through the copper wire has produced a magnetic effect. Thus, we can say that electricity and magnetism are linked to each other. Then, what about the reverse possibility of an electric effect of moving magnets? Okay. Can you please tell me about magnetic fields and electromagnetic effects? Sure. I shall also tell you about electromagnets and electric motors, which involve the magnetic effect of electric current, and electric generators, which involve the electric effect of moving magnets.
Magnetic field and field lines. We are familiar with the fact that a compass needle gets deflected when brought near a bar magnet. A compass needle is in fact a small bar magnet. The ends of the compass needle point approximately towards north and south directions. The end pointing towards the north is called the north-seeking or north pole. The other end that points towards south is called south-seeking or south pole. Through various activities, we have observed that like poles repel while unlike poles of magnets attract each other. Let's perform another activity. Fix a sheet of white paper on a drawing board using some adhesive material. Place a bar magnet in the center of it. Sprinkle some iron filings uniformly around the bar magnet. A salt sprinkler may be used for this purpose. Now tap the board gently. The iron filings arrange themselves in a pattern as shown. The magnet exerts its influence in the region surrounding it. Therefore, the iron filings experience a force. The force thus exerted makes iron filings to arrange in a pattern. The region surrounding a magnet, in which the force of a magnet can be detected, is said to have a magnetic field. The lines along which the iron filings align themselves represent magnetic field lines. Let's view another method of obtaining magnetic field lines around a bar magnet with the help of an activity. Take a small compass and a bar magnet. Place the magnet on a sheet of white paper fixed on a drawing board using some adhesive material. Mark the boundary of the magnet. Place the compass near the north pole of the magnet. The south pole of the needle points towards the north pole of the magnet. The north pole of the compass is directed away from the north pole of the magnet. Mark the position of two ends of the needle. Now move the needle to a new position such that its south pole occupies the position previously occupied by the north pole. In this way, proceed step by step till you reach the south pole of the magnet as shown. Join the points marked on a paper by a smooth curve. This curve represents a field line. Repeat the above procedure and draw as many lines as you can. You will get a pattern shown. These lines represent the magnetic field around the magnet. These are known as magnetic field lines. Observe the deflection in the compass needle as you move it along a field line. The deflection increases as the needle is moved towards the poles. Magnetic field is a quantity that has both direction and magnitude. The direction of the magnetic field is taken to be the direction in which a north pole of the compass needle moves inside it. Therefore, it is taken by convention that the field lines emerge from the north pole and merge at the south pole. Inside the magnet, the direction of field lines is from its south pole to its north pole. Thus, the magnetic field lines are closed curves. The relative strength of the magnetic field is shown by the degree of closeness of the field lines. The field is stronger, that is, the force acting on the pole of another magnet placed is greater when the field lines are crowded. Magnetic field due to current carrying conductor. In order to find the direction of the field produced, let us repeat the activity in another way. Take a long straight copper wire, 2 or 3 cells of 1.5 volts each, and a plug key. Connect all of them in series as shown. Place the straight wire parallel and over a compass needle. Plug the key in the circuit and observe the direction of deflection of the north pole of the needle. If the current flows from north to south, the north pole of the compass needle would move towards the east. Replace the cell connections in the circuit. This would result in the change of the direction of current through the copper wire, that is, from south to north. Observe the change in the direction of deflection of the needle. You will see that now the needle moves in the opposite direction, that is, towards the west. It means that the direction of magnetic field produced by the electric current is also reversed. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. We shall first consider the pattern of the magnetic field around a straight conductor carrying current with the help of an activity. Take a battery, 12 volts, a variable resistance or a rheostat, an ammeter, 0 to 5 amperes, a plug key, and a long straight thick copper wire. Insert the thick wire through the center, normal to the plane of a rectangular cardboard. Take care that the cardboard is fixed and does not slide up or down. Connect the copper wire vertically between the points in series with the battery, a plug, and key. Sprinkle some iron filings uniformly on the cardboard. Keep the variable of the rheostat at a fixed position and note the current through the ammeter. Close the key so that a current flows through the wire. Ensure that the copper wire placed between the points X and Y remains vertically straight. Gently tap the cardboard a few times. Observe the pattern of the iron filings. You would find that the iron filings align themselves, showing a pattern of concentric circles around the copper wire. These concentric circles represent the magnetic field lines. The direction of the magnetic field can be found by placing a compass at a point, say P, over a circle. Observe the direction of the needle. The direction of the north pole of the compass needle would give the direction of the field lines produced by the electric current through the straight wire at point P. Show the direction by an arrow. If the current is increased, the deflection also increases. It indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. If the deflection of the needle, if the compass is moved from the copper wire, place the compass at a further point from the conducting wire, say at point Q. We see that the deflection in the needle decreases. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it decreases. A convenient way of finding the direction of magnetic field associated with a current-carrying conductor is right-hand rule. Imagine that you're holding a current-carrying straight conductor in your right hand such that the thumb points towards the direction of current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field. This is known as the right-hand thumb rule. Magnetic field due to current through circular loop. We know that the magnetic field produced by a current-carrying straight wire depends inversely on the distance from it. Similarly, at every point of a current-carrying circular loop, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. By the time we reach the center of the circular loop, the arcs of these big circles would appear as straight lines. Every point on the wire carrying current would give rise to a magnetic field appearing as straight lines at the center of the loop. By applying the right-hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. We know that the magnetic field produced by a current-carrying wire at a given point depends directly on the current passing through it. Therefore, if there is a circular coil having n turns, the field produced is n times as large as that produced by a single turn. This is because the current in each circular turn has the same direction, and the field due to each turn then just adds up. Magnetic field due to a current in a solenoid. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. The pattern of the magnetic field lines around a current-carrying solenoid. The pattern of the field with the magnetic field around a bar magnet is similar to this pattern. In fact, one end of the solenoid behaves as a magnetic north pole, while the other behaves as the south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same at all points inside the solenoid. That is, the field is uniform inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material, like soft iron, when placed inside the coil. The magnet so formed is called an electromagnet. Force on a current-carrying conductor in a magnetic field. French scientist André-Marie Ampère, 1775 to 1836, suggested that the magnet must also exert an equal and opposite force on the current-carrying conductor. The force due to magnetic field acting on a current-carrying conductor can be demonstrated through the activity. Take a small aluminum rod AB of about 5 centimeters. Using 2 connecting wires, suspend it horizontally from a stand. Place a strong horseshoe magnet in such a way that the rod lies between the 2 poles with the magnetic field directed upwards. For this, put the north pole of the magnet vertically below and south pole vertically above the aluminum rod. Connect the aluminum rod in series with a battery, a key, and a rheostat. Now pass a current through the aluminum rod from end B to end A. It's observed that the rod is displaced towards the left. You will notice that the rod gets displaced. Reverse the direction of current flowing through the rod and observe the direction of its displacement. It is now towards the right. The displacement of the rod in the above activity suggests that a force is exerted on the current-carrying aluminum rod when it is placed in a magnetic field. It also suggests that the direction of force is also reversed when the direction of current through the conductor is reversed. Now change the direction of field to vertically downwards by interchanging the 2 poles of the magnet. It's once again observed that the direction of force acting on the current-carrying rod gets reversed. It shows that the direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. Experiments have shown that the displacement of the rod is largest or the magnitude of the force is the highest when the direction of current is at right angles to the direction of the magnetic field. In such a condition, we can use a simple rule to find the direction of the force on the conductor. We considered the direction of the current and that of the magnetic field perpendicular to each other and found that the force is perpendicular to both of them. The 3 directions can be illustrated through a simple rule called Fleming's left-hand rule. According to this rule, stretch the thumb, forefinger, and the middle finger of your left hand such that they are mutually perpendicular. If the first finger points in the direction of the magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor. Summary. Let's summarize the topic. Magnetic field has both direction and magnitude. The direction of the magnetic field is taken to be the direction in which a north pole of the compass needle moves. A circular coil having n turns, the field produced is n times as large as that produced by a single turn. A strong magnetic field produced inside a solenoid used to magnetize a piece of magnetic material.